Hello everyone. In this class, we will learn regression. We will review our correlation in class exercise 3. Then we talk about what is the best fitting line, the rationale for choosing the best fitting line. We will explain how to compute the regression equation, including how to compute the intercept and the slope. Then, given an x, how to use the regression equation to predict y. Next, we will explain the connections between regression and correlation. What is the relationship between R and B? What is the scatter plot and the best fitting line? Finally, we will run regression with SPSS. Take out the in-class exercise 1.3 you did last class. In this example, Wagner investigated the relationship between stress and mental health in first-year college students. There are two variables. Variable X is stress. It is measured with number of negative life events reported by college students. Variable Y is psychological symptoms measured with Hopkins symptom checklist. To calculate the correlation between variable X and Y, we first compute the covariance, the degree to which two variables vary together. This is part of the dataset collected by the researchers. The first column indicates number of participants. The second column is variable stress, and the last column is variable symptoms. This is log transformation symptoms. As you may remember, this is the conceptual formula for covariance between X and Y. In this in-class exercise, you will be using the computational formula to get the covariance between X and Y. The computational formula, you will need three pieces of information. First is sigma x, adding all x together, this is 2,278. Second is sigma y, adding all y values together, you will get 479.668. Then it is sigma x times y, it is 10,353.66. Covariance equals to sigma xy minus sigma x times sigma y divided by sample size, then divided by n minus 1. Therefore, covariance equals to 10,353.66 minus 2,278 times 479.668 divided by 107. Then the denominator is 107 minus 1. The covariance is 1.336. From here, you can compute the correlation coefficient. The handout gives you the standard deviation of X, which is 12.492, and the standard deviation of Y, which is 0.202. Therefore, correlation coefficient is 1.336 divided by 12.290 times 0.202, which is 0.53. Next, you were asked to test the significance of the correlation coefficient. We follow 4 steps. First is to form the research hypothesis. The null hypothesis is rho equals to 0. The research hypothesis is rho does not equal to 0. Second, we need to set the decision criteria. Alpha by default is 0.05. This is a two-tailed test. Degree of freedom is sample size 107 minus 1 minus 1. So DF is 105. If you look at the T-critical table, T-critical is positive and negative 1.98. Next, you conduct a t-test. T-observed score equals to 0.529 times square root of 107 minus 2. Then the denominator is square root of 1 minus 0.529 squared. So T-observed score is 6.38. Because T-observed score is greater than the positive T-critical score, we reject the null. Then we report the results in APA style. We reject the null hypothesis. Stress was significantly related to psychological symptoms. R is 0.53, P is less than 0.05. To run correlation with SPSS, you need to open the SPSS data file. First, you take a look at the data set, examining the sample size, data range, missing values. Then last class, we explained how to conduct the log transformation of symptoms. You can follow these steps to create a new variable, which is called log symptoms. Then this is the Y variable you're going to use in running the correlation. After you creating the log symptoms, you can run correlation between stress and Y. Click on Analysis, then Correlation, then Bivariate. Moving stress and log symptoms and variables, click on Option, click on Means and Standard Deviations, then click on Continue and OK. This is the SPSS output. As you can see, the descriptive statistics displays the mean and SD of the two variables. Then the correlation between stress and log symptoms is 0.529. P-value is less than 0.001. So in APA style, you report stress was significantly related to psychological symptoms. R is 0.53. P is less than 0.001. Lastly, you were asked to create the scatter plot using SPSS. So you open the SPSS data file, click on Graphs, then Scatter /dot, then Simple Scatter. You click on Define, move stress to X-axis and log symptoms to Y-axis, then click on OK. You should be able to create this scatter plot. We have spent a lot of time explaining correlation and explaining how to compute the correlation coefficient between two variables. This correlation coefficient can also be influenced by a few factors other than the real relationship between X and Y. The first factor is called range restrictions. So what is range restriction? When you measure a variable, the possible range may be from 200 to 800, but due to some limitation of your data file may only contain a fraction of that range. When this happens, this will affect the correlation coefficient you compute based on this data file. Let me give you an example of range restriction. Suppose you want to study the relationship between GRE verbal score and the GPA. GRE verbal score, this is the old system. It ranged from 200 to 800. So students took the GRE verbal test and they were selected into graduate school. Then you also collected their GPA in the first year of graduate school. So as a researcher, you want to examine if the GRE verbal score is significantly related to graduate students' first-year GPA. X-axis is GRE verbal score. The full range is from 200 to 800. Then Y-axis is graduate school GPA. The full range is from 0 to 4. As you can see, ideally, you want to collect people scored very low versus very high on the GRE verbal test. And if this is the case, the full scatter plot, if you look at the test score, which is the x-axis, it ranged from 200 to 800. Then GPA ranged from 0 to 4. And if you look at the whole scatter plot, there is a positive correlation between GRE verbal score, test score on the x-axis, and the GPA. The correlation is 0.65, which is moderately high positive correlation. However, in reality, when graduate school selected students to their program, they have a cutoff on GRE score. Suppose this cutoff is 400. Only students who received 400 and higher will be selected into the program, and only these students will be able to provide their first-year GPA score. Therefore, in reality, your dataset will only contain GRE verbal test from 400 and up. Your dataset wouldn't have anybody who scored lower than 400 because 400 is a cutoff score. When this happens, your scatter plot actually looks like the one at the right of the dashed vertical line. And the correlation based on this fraction of the data points is only 0.43. So as you can see, the range restriction actually affected your correlation coefficients. It most likely will reduce the correlation coefficient between X and Y. Another factor that may affect the effect of a correlation is the effect of subsamples. Sometimes you collect data from a sample, but this sample might be comprised of different subsamples. The correlation between height and weight may be different across different subsamples. Here is the scatter plot between height and weight. Data from males is labeled by the solid red dots, and data from females is labeled by the squares. If you look at all the scatter plot, including both female and male data points, the correlation was as high as 0.78. However, if you just look at the male data, the toward the upper right corner, for male, the correlation between height and weight is 0.60, and for female, the correlation between height and weight is 0.49. Therefore, if you use 0.78 to estimate the correlation between height and weight for different subsamples, male versus female, you would make some errors. Therefore, different subsamples may affect how you estimate the correlation between X and Y. So, range restriction and different subsamples are two possible factors may influence the correlation coefficient you get from your sample.